take a look into that. Okay, somewhat reasonably okay kind of it. Maybe 30-40% of the students have joined. Now let me go ahead. So at some other point of time, you can download these two and then start reading. So mostly, actually, you have another 4 weeks time for the next mid examination to begin. All of you may have to start seriously. As far as OS is concerned, those two chapters, this is the textbook prescribed. Just go through that. It is very easy to read, and some of you might have already completed even operating systems. But even if you have not studied earlier, by just reading that, you will understand. And I'm also like giving the general idea so that when you go through the book, you will better understand. Okay. So let me complete that program later on, maybe for some more people to join. But meanwhile, let me begin the go through the corresponding slides themselves. Right. So whatever slides that I am just giving you, the same slides I'm going to open, and then let us actually start understanding what those things are. Okay, so this is the actual slides, as you can see. So these are the various things what you can have it. Only what is that an operating system will do. And in order to develop an operating system, you require some support, right, from the computer organization. What kind of support do you require from the processor? So that also will be talked about. And various other device managements, including the process, memory, storage, protection and security kind of things. So objectives of the course is to provide a grand tour of major components of the operating system, overview of the many types of computing environments. Computing environments means you have computing environments right from starting from your mobile. Your mobile also is a computing environment where you can do small things. Even your mobile has got an operating system. So popular operating systems for mobile systems are, one is mostly Android operating system, right? That's what most of you might be using. And there is another one like what you call iPhone. So iPhone uses iOS, it's called as actually iOS operating system. So mostly both of them are somewhat closely related to Linux-like operating systems actually, both. The background of your Android operating system as well as your even iOS is taken from Unix or Linux operating system like thing mostly. And for PC segment, you also have Windows 10 kind of thing, all those things. So computing environment, you're talking about mobiles is one thing, and then the other thing can be your tabs kind of thing, embedded systems like in a car, when you are driving a car, so you will see a dashboard there, lot of details are going to be displayed using digital kind of interfaces. So even that will have a kind of an operating system built into that. Those are sometimes called as embedded systems. So even their popular operating system is Linux only, once again, mostly. And then you have laptops or desktop environments where individual users can make use of them both for development purpose as well as for entertainment purpose and other details. And then you have servers. So which are going to provide various services to multiple users. Most of the time, servers will provide services to multiple users at like a kind of simultaneously kind of thing, right? So like this, there are different computing environments. All of them require operating systems there and all that. And then you are also saying open source operating system. There are two types. One is open source, where the operating system is freely available and no maintenance will be there, in fact, but you must have minimum knowledge of maybe downloading what to be downloaded and how to install it and how to start using it and so on. And nobody is going to come to you and then install and all that kind of thing. And the corresponding source code also is made available in case you want to make changes and then have your own type of operating system. All those things are allowed in the open source operating systems. Again, Linux is one example of open source operating system. So, and the other one is proprietary operating systems. Proprietary meaning that you you need to buy the operating system from some of the vendors, some of the companies kind of thing, or maybe distributors kind of thing. So you have to pay for it, and then they will maybe deliver the operating system in the form of a media, whatever. Sometimes they might even send their people to help you to install and all that. And for all that, they charge and all that. So those are two different models that you have. And what is an operating system? Already, as I said, there are many definitions. There is no single definition for that, and one need to understand. A program that acts as an intermediary between a user of a computer and the computer hardware. Right? Directly, computer hardware cannot be used, and in between you have the operating system will act as an interface between the user and computer hardware. What are the goals? So the operating system will make the users to execute their programs and make solve user problems easier and all that. Make the computer system convenient to use, easy to use kind of thing. Use the computer hardware in an efficient manner. Efficiency also is one of the criteria of the design of the operating system. So more importantly, when in the earlier days, computers used to cost very high. In those days, people used to give more importance to efficiency because they need to engage more people, more users should be allowed to run their programs and all that, rather than the convenience there. So optimization in terms of efficiency used to be the criteria in the earlier days, but as the computers cost become less and less, and compared to that, people cost is more and more. So the operating system design goals is shifted even to user interfaces, better user interfaces, so that it becomes straightforward for the user to straight away start using it, right? So a lot of developments, both in terms of input-output devices. At some point of time, there was no mouse kind of thing. Only input device used to be the keyboard kind of thing, right? So later on, a mouse has come and several other like touch pads. Now touch screens also have come. So like that, so many changes have come in the last maybe 40 years, you can say. Unbelievable changes. So the same thing, like you will also find them as a part of the operating system as such. So computer system now can be divided into 4 components. I'm actually now going through the book. So I've already talked about all this in a general way in the last class, but now I'm opening it so that like for you, the resource also is available later on. So computer system can be divided into 4 components. Hardware provides basic computing resources. Central processing unit, memory, input output devices. These are the hardware components. And then operating system controls and coordinates use of hardware on various applications and uses. The third one is application programs. 4 components, out of them 1 component is the hardware, the second is the operating system, Third is the application programs. The fourth one is actual users themselves. Users sometimes might be machines also sometimes, because it's possible for machine to machine communication. And then one machine, a program running on one machine can request a program running on another machine to maybe execute something and so on like that. So these are the four components. A diagram also you will see in the next slide kind of it, and what each one of them are going to do and all that particular. It is so easy for all of you to understand, because all of you have already seen like what a computer is and all that. So you can easily relate all this discussion to what you are already using a computer there and all that. So this is the diagrammatic representation of that. You have a computer hardware at the lowest level, at the core of it. So on top of it, you develop an operating system for that particular hardware. And apart from the operating system, you also provide programs, so that programs can be used to execute and then get the feel of it. So those programs are of two categories: system and application program. System programs normally come along with operating system. Application programs, depending upon your requirement, you might buy them. Simple examples maybe your application programs can be your word processor or spreadsheets, PowerPoint presentations. These are all application programs. They don't come with the operating system. So whereas just like listing the files, or like copying files from one location to one device to another device or whatever. So, and then connecting what it is, your computer to the network, all these things are the system programs themselves. And even the compilers, assemblers, editors, they are all a part of the operating system mostly. So you can see here system and application program. Under this category, you have compilers, assemblers, text editors, database systems, and even other like spreadsheets and all those things. So several users can simultaneously be connected to the same system, provided the operating system is designed for multi-user environment. So several users can simultaneously connect to that and then start using it. But you also have single user environments like a simple personal computer system and all that, where only at any point of time one user is going to make use of it. It is highly personalized system, all the resources, everything. So operating system, what do they do, right? So that's what he is talking about. Depends on the point of view. So one thing is the users want convenience, ease of use, and good performance. These two. Performance wise, it must be better, and usage wise, it should be easy to learn, quick, like very quickly one should be able to learn them. Don't care about resource utilization. This is one one side of it. Mostly nowadays the trend is that. Trend is ease of use, good performance, resource utilization. Olden days, but shared computers such as mainframes, mini computers must keep all users happy, because they are multi-user environment. When there are several users, you cannot be biased towards one particular user. You want to give access to the resources in a fair manner, so that in a transparent manner, so that all the users feel at home that yes, their service is being honored by the computer system. Right? So that used to be the earlier days. But now, like when individual system you have it is naturally easy to design it so that like all the resources are with you, and user interfaces like mouse, touch screen, such kind of things are also provided for ease of use. Users of dedicated systems such as workstations, they are of a different nature, like have dedicated resources but frequently use resources on the net to connect to the servers and all that. So workstations are different. They are bigger systems than your personalized computer system, but at the same time, like only individuals are going to use the workstations, just like a personal computer. But workstation is almost as powerful as a server kind of thing. So that's why that is again like it is more dedicated system. for running complex programs that may require the entire system to be available for that running that particular program alone. So in such cases, you go for workstations. Most of the times, like your uh, GIS, Geographical Information System, GIS based systems and all that, they use workstations. And then handheld computers are resource poor. Not many resources are available. For example, power wise, very little. Like once you charge, you can use for maybe let us say 4 hours or 10 hours, and after that again you need to charge. So and the screen size may be small, right? And all those related issues related to small devices, handheld computers, optimized for usability and battery life. And some computers have little or no user interface, such as embedded systems. So there won't be any user interface, very little or may not be at all, because it's going to take care of the functions that it is designed for. For example, you might have an embedded system to give you what is the speed at which the automobile is running. So it's going to continuously give you the corresponding thing. So there may not be any user interface for that particular thing. If at all it is there, you are likely to choose whether to display in kilometers or miles, that kind of stuff. So compared to the other device systems, here there will be very little user interaction. So these are the various types of computing environment, right from small embedded systems, handheld computers, workstations, servers, mainframe. You see, these are all the computing environment. And for all of them, you require different operating systems with different specifications, different functionalities, and all that particular thing. So OS is a resource allocator. Slowly definition you are trying to give. It manages all resources, decides between conflicting requests for efficient and fair resource use. And OS is a control program, controls execution of programs to prevent errors and improper use of the computer. Right? So it's going to give access to several users and see that they use the resources, devices in a manner that they are designed for. So all that operating system is going to actually do that. And as you can see again, now he is saying no universally accepted definition. There is nothing like that. You can start talking about it. It's almost like a human being. What kind of definition are you going to fit in? Right? So we don't because depending upon the way you look at it, you are going to specify that particular thing. So one person might be a doctor, the other one might be an engineer, another person might be a politician, so and so on. So there are different definitions there depending upon the angle with which you look at it. Similarly, operating system also. So at the end, what he is saying is that everything a vendor ships when you order an operating system is a good approximation. It is you order an operating system to a company, whatever they are supplying, right, and what it is going to do it is what that operating system is. The one program running at all times on the computer is the kernel. So within the operating system, there is an important portion which we call it as kernel, right? It is the core of the operating system, and that will always be running, and that is the one that is providing services to all the users. All the users, meaning that strictly speaking, all the programs will request for the operating system services, kernel services. But the programs will be executed by the end users. So end user is communicating to the operating system by running a program. And the program while running is going to make request to the kernel to give various services. That's what it is actually. So everything else, right? Everything else apart from the kernel, everything else is what? It is a system program. So or an application program. That's what you have already seen there, right, in the diagram, right? So this operating system is actually giving another name to this as a kernel. Everything else, as you can see, system and application programs. So the other day we have already again talked about, because all your computers are based on von Neumann architecture. Von Neumann architecture means your processor can run a program only when the program is loaded into the memory, main memory. It cannot directly execute programs from the secondary storage. So that means your operating system is available on the secondary storage, strictly speaking, right? Because that is the area where your program can be stored, even when you switch off the system. It is a persistent memory, not non-volatile. Volatile means when you switch off the power to that, everything that you stored there is lost. Non-volatile means even when you switch off the power supply, the data that you store there is going to be still available. So, in the secondary storage, your operating system is there, but it cannot be directly executed. So, you require some mechanism of storing your starting instructions that need to be executed to load the operating system from the secondary storage and then start executing. And that starting program is called as bootstrap program. And normally it is available on the read-only memory or erasable programmable read-only memory. These are sometimes also called as firmwares. Hardware, software, firmware. Hardware is pure hardware. Software is pure software, only instructions. Firmware means both hardware and software, both combination. So this EEPROM is actually, because what is the hardware here? Hardware is your ROM. But what is the software there? Whatever the bootstrap program that you are loading into that is your software. So that's why it is called as a firmware, another technical term that you are actually using. So when you start your system, your processor is designed such that it actually fetches the instruction from the ROM, from the read-only memory. Fetch the first instruction, fetch the next instruction, and keep initializing all the parameters of the devices and all that, and then start loading operating system from the secondary storage. All that is going to happen there. Initializes all aspects of a system, loads operating system kernel, and starts execution. So this firmware, this bootstrap program will load the operating system kernel from the secondary storage into the main memory. But that main memory is volatile. Once you get it into that, and then once again, in case you switch off the system, whatever you have brought in is lost again. So that's why next time again you have to bootstrap. So that is how the computer startup is going to happen. So computer system organization, how are you going to connect various devices and then make a computer system? So that is the assumption with which your operating system is going to be designed, how they are all connected physically and all that. Then the OS instructions are going to be designed such that it can start making use of it. So this is a general diagram of a computer system organization. As you can see, the memory is a place where you can store and retrieve information, and that is accessible to all the IO devices as well as the processor, central processing unit. Because like if the CPU would like to read something from a disk, see, all of you need to understand these devices operate at different speeds. The speed at which the CPU can perform is very high compared to the speed at which these input-output devices can provide the data. That's why directly they are like central processing unit doesn't communicate with disk or input-output devices. So for every input-output device, there will be corresponding associated memory. And that memory you normally call it as a buffer actually. So that if the input-output device wants to provide a data to the CPU, it doesn't directly provide, but instead it's going to place the data into the buffer, into the memory. because the memory and the CPU, they work at reasonably similar speeds. Whereas IO devices maybe in terms of hundreds or thousands of slow compared to the speed at which CPU works. So in order to utilize the CPU properly, you manage a buffer there. For every device, you keep a buffer so that the device will store the data into the buffer and CPU will pick the data from the buffer. That is how the coordination is going to happen. So the diagram here is CPU here, disk controller, and all your magnetic disks. So whatever disk storages which are non-volatile in nature, and then USB controller. And onto the USB interface, you can connect any of the USB kind of input-output device. So a mouse can be connected, a keyboard can be connected, a printer can be connected, which are supplied with a common interface with which the OS and the device can actually agree upon. It has become very popular these days. Not that USB is there right from the beginning. Maybe you can say hardly 15 years or so is the life of this USB kind of concept. So these devices you can connect, and there is a controller here. Controller is an electronic circuitry that's going to handle these devices about how to read the data or how to display the data or how to print it, that kind of stuff. And then you have a monitor here, and you need to display the all your results or whatever onto the monitor. So for that, you require again a card kind of thing, which you normally call it as a graphics adapter. Because this monitor is arranged as a pixels, a matrix of pixels. Monitor is considered as if it is a matrix of pixels. So many pixels will be there, like millions of pixels. Every pixel, you need to store the information about what data is to be stored there. So like a kind of a maybe what is the color with which it should be ignited there. So such kind of stuff will always be there as a part of it. So a lot of memory is also required for storage of for displaying that entire thing. So graphics adapter will have its own memory, in fact, in order to display that and so on like that. And apart from that, all these devices are connected directly to the memory, and they will be storing and retrieving information there and all that. So one or more CPUs. Nowadays, dual core, right? Dual core, quad core, like that. So when you buy a single, like normally motherboard, so on that you will have a processor that itself contains multiple central processing units within them. Because of the VLSI technology and so on, you can embed more and more CPUs within a single chip kind of thing. One or more CPUs, device controllers, connect through common bus, providing access to shared memory. Concurrent execution of CPUs or devices competing for memory cycles. All of them will be continuously be using them, like by making a request and then all that. So you have to actually design for efficient concurrent execution of CPUs and devices simultaneously. So now slowly you are talking about IO devices and the CPU can execute concurrently. So devices will be busy supplying the data that is requested while running the program by the central processing unit. So what is happening now? The CPU can make a requested device, and instead of waiting for the device to provide the data, so what people will normally do is CPU will switch to execute another program or to execute a thread within the same program. These two possibilities are there. So instead of wasting time there, so how is that possible? Because by designing your operating system so that you are going to load multiple programs into the memory simultaneously. right? Your operating system must be capable of loading multiple programs into the memory, because unless you load it, you can't run it. In fact, there used to be a time where, maybe 60 years back or so, there used to be a time where only a single program can be loaded and executed. Such programs, such operating systems, you call them as uni-programming operating system. Uni-programming operating system. Only one program can be loaded. CPU can execute that. In case the data is required, CPU requests that particular device, and it will be waiting, wasting all its time. And once the data is ready, and again it takes that, run that, and so on like that. But then, like, because of those days, in fact, those computers used to be very costly, running into crores. Not only that, they used to occupy a lot of space. So they were actually designed by making use of a vacuum tubes kind of thing, which require a lot of power, maybe as much power as required by one entire village nowadays. So go through that. It will be really thrilling to know the developments that have happened on computers from the days of 50s, 1950s to the current time. How the size of the computers used to be, how big it is. So how difficult people have actually went through, because they could see the impact that these computers could bring in future. So they might have started with adding 2 numbers, but investing maybe few, maybe tens of crores. That kind of money they have invested actually. So those are the visionary people who could see the kind of impact that such devices can bring in future, and the R&D can bring slowly, and the cost will come down. Many people will start using it. So all that they could visualize. So within a period of about maybe 50, 60 years. So we are fortunate enough to see the actual benefits there and all that. So go through that, like it will be a wonderful experience later on. So IO devices and the CPU can execute concurrently. Each device controller is in charge of a particular device type. Devices, normally you categorize them under 2 categories on one basis. One is character device, the other one is a block device. Character device means a device that can supply one character at a time, kind of it. So it is a kind of a serial device, kind of it. For example, your keyboard. From the keyboard, you can only provide one character at a time, right? You are typing one character at a time, kind of it. So such a device is called as character device. So the kind of drivers that you have to write is totally different there, the mechanism. The other one is a block device. Block device means you can read one block at a time from such devices. Either read or even write, for that matter. For example, like storage devices, your disk, magnetic disk. Whenever you want to read from a disk device, you cannot read a single character, even though you may require a single character, but you have to identify first which block or which sector that particular character is. And then that device will supply the entire block. And out of that, you have to pick whatever character within that particular block that you require and all that. So depending upon the device type, you have character devices and block devices. So go through that. And accordingly, the controllers have to be designed for that particular thing. Each device controller has a local buffer. That buffer is nothing but a memory. So that whatever is, like for example, you want to print something. If it is an output device, what CPU will do? CPU will only place the data that is to be let us say printed, right? So printer is a slow device. It's not going to supply like the data as and when it is printing. So that's why what it will do is the CPU will place all the data that it requires to be printed into the buffer first, because the speed at which the buffer can take is almost at the speed of the CPU. After putting the data into the buffer, then it initiates the device to print it. And then CPU will actually go on its own. Printer also will go on its own, because the printer is given the instruction to take whatever is there in the buffer and print it. And the CPU will move ahead, like, and do its own job there and so on. And whenever the device completes its job, whenever the printer completes it, then it's going to tell the CPU again, interrupt it. Interrupt the CPU saying that the job is done. Similarly, even for reading data also, it's going to make a request to a particular input device to read something. And then CPU will go ahead in doing some other program, executing that and so on. So once the data is ready, the input device again interrupts the CPU. See, you have asked me to read the data is available, please take it. Then the CPU is going to attend to that by using interrupt like what it is, service routine, whatever, and then do whatever is required. Because the moment the device interrupts it, data is already there in the buffer, and then it can simply pick that data and then move on very quickly there as a part of it. So IO is from the device to local buffer of controller. Device controller informs CPU that it has finished its operation by causing an interrupt and all. So these are all the presentations here, but in the textbook you can see a lot of further explanation there and so on like that. So go through that, read it, you will all be able to understand. And common functions of interrupts. So interrupt transfers the control to the interrupt service routine, right? So whenever an interrupt comes from a device, the CPU must understand what need to be done. So which program, like what need to be done means like what is the sequence of instructions that is to be executed whenever an interrupt comes. And such sequence of instructions we call them as interrupt service routines. So there will be a kind of interrupt vector, meaning that like if there are several devices, for every device there will be a different interrupt service routine. So device number 1, interrupt service routine starting address is going to be so and so. Device number 2, there will be another like a different interrupt service routine address for addressing that particular device. So interrupt vector means, so as many devices you have, vector is nothing but an array actually. So an array of service routines which contains the addresses of all the service routines. Interrupt architecture must save the address of the interrupted instruction. All that. A trap or exception is a software generated interrupt caused either by an error or a user request. Exceptions, right? The other day we were talking about exception handling, especially divide by 0. Such kind of any errors occur, there will be different service routines for those things also. So in other words, what you are indirectly saying that an operating system is interrupt driven. That is more important. It doesn't wait. The advantage of interrupt driven is that waiting can be cut down. Everybody is busy. CPU is busy, devices are busy, and whenever the devices are ready with something, they interrupt. That's CPU. Then the CPU is going to attend to that and quickly move on. That is the what it is, the design of the operating system. That is how it is built, so that there won't be any waiting for any waiting and wastage of the resources. Interrupt handling, the operating system preserves the state of the CPU by storing registers and the program counter. This all of you must be knowing. Whenever the CPU makes a call to another function or something, what it does, before moving and executing that particular function, first you have to save, because after completing the function call, you need to come back to the place where you are actually calling. So in order to come back to that, so what you normally do is you store all the registers as well as the program counter normally onto the stack. You maintain a stack and store all these registers and program counter. Normally you use the word like push all the registers and the program counter onto the stack, and go there to that particular service routine or whatever, execute all of them. And whenever there is a return statement, when there is a return statement there, you need to come back to the calling place. So how are you going to come back? By just simply popping out. Pop out all those registers as well as the program counter. popping out is nothing but filling back the registers and the program counter with details, as if you are with details that were there before initiation of the service routine. So that is how it is actually. Determines which type of interrupt has occurred, polling and vectored interrupt system, right? So there are different ways. In fact, sometimes polling is a kind of a non-interrupt based. That means the CPU itself is going to continuously. Like if your device cannot actually interrupt, it doesn't have the capability of that particular thing. Then polling is another technique actually. It's going to continuously examine each and every device. Do you have data? Do you have data? Do you have data? And so on like that. All the devices. So whenever a device like CPU asks a particular device, do you have something, and so on. When they respond, yes, it is, then it's going to this thing. That is what is called as polling. It is not an interrupt based, but polling based. It is not a preferred one mostly. Interrupt based is like the corresponding controller is going to generate the interrupt. Separate segments of code determine what action should be taken for each type of interrupt. So this is a kind of a diagram that you can see. The CPU here, where it is busy, where it is attending to the IO request and all that. Here IO devices. As you can see, normal scenario is that user process is executing. Let us say user process is executing here. And then here IO device. So at this level it is like idle. Bottom means it is like a device is busy. IO device is busy. Right here. So for example, the CPU is executing, it is running here. Coming to this point, CPU requires some data, let us say. So what it will do, the CPU makes a request to the IO device. Right now it is idle, but when it makes a request, then IO request is there. Then like after making a request, what the CPU will do? CPU will continue. CPU will continue. IO device also will continue. So IO is busy here, transferring the data or whatever. Processor also is busy here. After some time, as we can see, when you reach this point, transfer done. When you reach this point of transfer done, then at this point of time, the IO device makes an interrupt. This IO device interrupts this CPU. When you interrupt it now, as you can see, instead of running the user process, it is now attending to the interrupt service routine. That's why there is a dip here. It is attending to IO interrupt processing. This dip. After attending to that, this will again continue the execution of the user process. And here, device, because already entire data is supplied, so device will be idle again. So whenever, like as you can see, it is a CPU that is giving the work. Any questions there? It is a CPU that is initiating the IO request. How does the CPU know when to initiate IO request? It all depends upon the programs that you write. So if there is a read, read function, for example, your scanf will take care of, and it is directly initiating an input request from the keyboard or whatever. So automatically the CPU, the moment it executes, actually scanf is not a single instruction. At a higher level programming language level, yes, this is a single statement, high level language statement. But when you compile it and generate the machine code, that single scanf may actually run into a few tens of instructions, right? Close to hundreds of instructions kind of it. So there you are going to come across IO request and then transferring the data, accepting that, all that kind of thing. So this is a kind of scenario that you can easily understand. CPU going through that IO device. So you are making both CPU and IO device busy all the time whenever it is required. And now IO structure. So what all that you have here and all that. After IO starts, control returns to user program only upon IO completion. right? This is one possibility. After I/O starts, control returns to user program only upon I/O completion. Wait instruction idles the CPU until the next interrupt, right? And wait loop, contention for memory access. At most one I/O request is outstanding at a time, no simultaneous I/O process. In fact, this used to be at some point of time. The old operating systems used to be like this, where the CPU, like if there is only one program, as we said just now, uniprogramming, CPU has to wait. There is no other work. If there is only one program to be executed, so when there is an input requirement, CPU has to wait, keep waiting until the data comes. So that model is this particular state. The other one is after I/O starts, control returns to user program without waiting for I/O completion. See, you don't wait there, but you give the instruction to the I/O device and you continue. This is interrupt driven based, right? Interrupt driven based, you don't wait. Whereas the other this thing, you have to wait. These two models, but all the existing systems mostly use this particular model. And how are you going to make all that? System call. How do you make a request for anything? System call. Request to the operating system to allow user to wait for I/O completion. Device status table contains entry for each I/O device indicating its type, address, and state. Right? For every device, you have a device controller. So it maintains the corresponding table will contain all the related details. OS indexes into I/O device table to determine device status and to modify table entry to include the interrupt. So those are all the details about how I/O is handled. One based on by keep waiting, and whenever comes you just proceed. The other one is you initiate and without waiting move on to executing another program. Storage definitions and notation review. These are all simple numbers kind of thing. Bit means all of you are aware of. One bit is either a 0 or 1 is going to be stored there, a single bit. 1 byte stands for 8 bits. All of you are aware of. 1 nibble means 4 bits, in fact. Less common term is a word. Word stands for sometimes like 8-byte words. Sometimes it's possible even 2-byte words also. It all depends upon the architecture that you have. Right? If it is a 64-bit memory, one word stands for 64-bit or 8-byte words. Right? So depending upon the data bus, what is the size of the data, how many bits. So that is a corresponding this thing. The computer storage along with most computer throughputs, these are the things. 1 kilobyte is KB. B is capital B. And sometimes B is written as small b also. Capital B means byte. Small b means bit actually. While representing these things, if you write capital K small b, kilobit it is actually. Capital K capital B, kilobyte. Megabyte is MB, gigabyte is GB, terabyte and petabyte. So all of you must be familiar with these things slowly. So especially all the storage you represent in terms of bytes, and your speeds, network speeds, data speeds, they are represented in terms of bits actually. Right? So network speeds are represented in terms of bits, kilobits. Mbps means 1 million bits per second, not bytes there. Right? So that all of you need to be familiar with. Storage structure. So there are different storage mediums. So you can just a hierarchy of structure, hierarchy of storage structure, normally you call it. Main memory, only large storage media that CPU can access directly. It is randomly accessible. You can access any part of the memory and find out what data it is. And the nature of that is typically volatile in nature. You cannot maintain the data once you switch off the power supply. Secondary storage, extension of main memory that provides large non-volatile storage capacity. And hard disk, rigid metal or glass platters covered with magnetic recording material. Right? So a kind of a magnetic coating will be given on the plate like material, very thin magnetic coating actually. And on that you can actually store 0 or 1 by actually storing something like what it is. You magnetize that part of it in a clockwise direction or anti-clockwise direction. Disk surface is logically divided into tracks, which are further divided into sectors. Because the capacity is so big that for manageable purposes, you are basically dividing all that. Ultimately, the minimum manageable unit under the disk is a sector. Whereas under the main memory, minimum manageable unit is a byte most of the times. 1 byte kind of. Whereas here it is a sector. The disk controller determines the logical interaction between the device and the computer. Nowadays, like a little bit more faster disks are coming, which are called as solid state disks. SSDs normally you call it. They are faster than the hard disk and still they are non-volatile. Various technologies becoming more popular. So cost is more. So you always make a judicious choice of what to do and all that. Storage systems organized in a hierarchy. So their nature, certain structures, storage systems are like what are the parameters? Speed at which the data can be supplied to the system, or take this or store this data into the system or whatever. And then what is the cost per unit of memory or whatever. And volatility, non-volatility kind of. These are the parameters to decide which one you require and all that. Caching is another popular word that you use so that you try to improve the performance of the system by judicially having a proper mix of these different storage devices. So you cannot have the complete thing as the main memory only. But main memory speed is much lower compared to the CPU. So for that, what people do is they maintain another type of memory called as cache memory. Cache memory is again like main memory only, volatile in nature. But the thing is, they are much faster, almost closer to the speed at which the CPU can actually work on. Whereas CPU directly taking the data from the main memory, it's again maybe very slow kind of thing. So that's why there is a caching mechanism, copying information into faster storage system. Main memory can be viewed as a cache for secondary storage. Right? That's natural, right? Compared to the secondary storage, if you consider secondary as the main, then the main memory becomes the cache itself. Whereas the cache memory is much faster, in fact, compared to the main memory. So device driver for each device controller to manage I/O provides uniform interface between controller and cache. So this is the storage device hierarchy. All of you need to understand. Magnetic tapes are used for backup purposes, to take backups of various data and program. But what is this thing? Their capacities will be very large. Storage capacity will be very large, but the speed at which the data can be stored or retrieved is very slow. So in the hierarchy, if you just take a look into it. Similarly, cost-wise also is going to be very cheap. Magnetic tape per unit cost is going to be much cheaper. The next level is optical discs, right? So whose storage capacities may be smaller than magnetic tapes. Cost-wise, it is higher compared to magnetic tape, and speed-wise, it is faster, right? Because optical discs are random access in nature. You can access any particular sector, so and then read it. Magnetic tape serial in nature. Continuously, it is like your audio tapes. You must have seen in case. So it is serial in nature. You can't jump. You need to continuously this thing. Very slow. So optical discs are external in nature, much slower compared to a hard disk. Hard disk is built into the system. and its cost is much higher compared to the optical disk. Solid state disk is even costlier than hard disk, but much faster because there is no like what you call moving parts within the solid state disk. You can think of as if solid state disk is almost equivalent to what you call these things, uh, memory devices, right? A small memory, this thing which you normally insert even to your smartphones and all that. So such kind of memory, almost with that particular size, in fact, you normally find it, solid state disk. Memory sticks also sometimes we use, so it will be of that particular nature. Hard disk normally contains moving parts. In order to move the read-write head from one track to another track, moving parts will be there. You require a fan and all that. There will be a lot of other associated mechanism. So solid state disk is much faster. Cost-wise, it is costlier, no doubt. So that's why, like always, a little bit of, for example, you can say 20 GB of solid state disk and 1 terabyte of hard disk. You can always have, so that your operating system can be stored on the solid state disk, and whenever you boot it, you are going to boot from solid state disk. So it will be loaded very quickly, and then the system is ready, right? Whereas all your programs, your much larger data and all that might be stored in the hard disk, right? Whereas actual like day-to-day programs which you require on a day-to-day basis can be stored on solid state disk. So a kind of a biomix can improve the performance. And directly you can't run programs from the solid state disk. You have to load into the memory. But main memory also is much slower compared to the speed at which the CPU can run. So that's why you require a cache memory. Most of the time, this cache memory is a part of the processor itself nowadays. So L2, like these things are again called as levels. L1, registers are internal to that. It is called as L1 memory. Cache memory is called as L2 memory. Main memory is L3, like that. So these are all levels. Some numbers are also given to those things. In the industry, whenever you go to a company and all that, you ask for L2 memory. Cache is nothing but L2. And then L3 is that, and so on. Caching, important principle performed at many levels in a computer, right? Information in use copied from slower to faster storage. Faster storage checked first to determine if it is already there in the faster storage, you make use of it. If it is not, you have to load from the slower one into the faster and all that. So there is a kind of a algorithm or a kind of a program that will decide where to search. Always search will happen within the cache. If it is not there, then cache failed, right? You fail to retrieve the data. So you have to now somehow get it from the main memory into the cache and then all that. So there is a lot of discussion on that and so on. Direct memory access, DMA, is another important architecture principle that is used in computer systems, so that for faster, quicker data transfer, normally you use DMAs, especially with these storage devices like SSDs, and even with your hard disk and so on, you make use of DMA. So used for high-speed I/O devices able to transmit information at close to memory speeds. Device controller transfers blocks of data from buffer storage directly to main memory without CPU intervention. Only one interrupt is generated per block rather than the one interrupt per byte. So whatever the CPU has to do, the device also is capable of doing that. The device controller will place all the data, whatever is required, directly onto the main memory. So instead of the CPU working on that particular thing. So CPU will instruct the DMA controller to transfer so and so information into so and so memory, like this many number of bytes. So such kind of things normally you use for faster and larger blocks of data. DMA is going to be used. So there is another DMA controller for that. how a modern computer works. So this is a von Neumann architecture like I have been talking about. So this is what it is. Instructions and data and the main on the main memory. This is the memory. This is your processor. So there are several devices. So in the memory you have instructions and data. What the CPU will do is within the CPU you also have a part of it is a cache, as you can see. So the processor will bring the instructions from the main memory into the cache. So instruction execution cycle and the data movement, whatever. So while doing this, it might like request the devices and so on like that. Sometimes DMA, like devices, can directly store the data into the memory. That is possible by using DMA, direct memory access. Whereas devices might supply the data through the CPU by using the interrupt mechanism. That's why here IO request. CPU makes an IO request, device makes the data ready, and then interrupts. And then the CPU copies that into the main memory or whatever that it is going to do. This is a von Neumann architecture. So he is the main person who has thought about how a processor should be there and all that. Even now we are continuing. All the processors are designed following his model of computer. So people actually thought about various models. Ultimately, this has become the popular one. Computer system architecture. Most systems use a single general purpose processor and have some special purpose processors as well. General purpose means programmable kind of thing. There are some other type of processors normally. For example, numeric processors. So you have processors that are specialized in doing the calculations, scientific calculations. They are called as numeric processors. Normal general purpose processor is capable of only doing arithmetic like addition, subtraction, multiplication and division. Whereas numeric processors, they are also sometimes called as co-processors. Co-processors, right? It's like they have the computing capabilities, but those things are specialized in nature. Only when demanded by general purpose processor, they are going to perform that. You have co-processors like one is a numeric processor for doing arithmetic, specialized arithmetic and all that. And you also have like IO processors, which are capable of doing some data processing kind of thing. Graphic processors also you have nowadays. So graphics cards you have a processor on that, and it can actually interpret all the various instructions related to drawing lines, drawing circles. That kind of things can be interpreted by your graphics processors also. They are sometimes graphics cards, you normally call them. On the card, you will have a processor. So there are different processors along with general purpose processors. Multiprocessor systems growing in use and importance, also known as parallel systems, tightly coupled. Advantages include increased throughput, economy of scale, increased reliability, graceful degradation or fault tolerance. Especially when like you want certain computing to happen in a real world scenario, it should not fail, right? Failure means a disaster, like in a furnace or some kind of industry area, right? You cannot, you want a system, a fail-proof system. And that is not possible by just simply having a single unit. Any physical device like is likely to fail at some point of time. But as a part of the design, you can include such that you, instead of having a single device, you can have two devices or two components, so that even if one component fails, the other component will take care of it. So that is how you design the fault tolerance into the system. So when both the components will be active, but only one will be servicing, and whether the other one is providing service or not, and whenever this detects that the other one is not doing that, this will take over that. right? Increased reliability, graceful degradation or fault tolerance. So in such cases, you are going to actually do that. That is another possibility. Asymmetric multiprocessing, symmetric multiprocessing. Each processor is assigned a special task. In the case of asymmetric, symmetric means every processor is capable of doing the same thing, same thing. Each processor performs all tasks. Symmetric means. Asymmetric, one is going to likely supervise and the other things. So that's what you mean by. So there are two types of parallel systems, of which there may be many processors, out of which one is going to be doing a special task, the other process might be doing common task kind of thing. Symmetric, all the processors will perform the same task. Symmetric multiprocessing architecture will be like this. You have several CPUs, but they are all having access to the same common memory. But each CPU will have its own cache, and it's going to perform that. Dual core design, within the same chip, you have two cores, core 0, core 1. Multi-chip and multi-core chassis containing multiple separate systems. Clustered systems, like essentially you need to connect a number of computers together, and all of them together are going to run a single program. That is also possible, like multi-processor systems, but multiple systems working together, running a same single program, but sharing a part of it. Usually sharing storage via storage area network provides a high availability service which survives failures. That is one advantage of having a cluster. Cluster means a group of systems doing the same task. Asymmetric clustering has one machine in hot standby mode, right, where it always continuously monitor and take over when something fails. Symmetric clustering has multiple nodes running applications monitoring each other. Some clusters are for high performance. Application must be written to use parallelization. Right? Your programs must be written so that they can make use of the cluster design. They can distribute the work. Your program is designed so that, like that. Right? All those things are possible. So this is a diagram for clustered systems. 3 computers are connected, interconnected, and all of them have a common storage area network. Right? So they all have a same external storage. That's what you mean by secondary storage. So they can all share the common data and then work on a common problem. This is what you mean by cluster. Now this is the actual, in the very beginning itself, we must have actually this thing told. These are some of the definitions basically. Operating system structure. What do you mean by that? Multi-programming, right? This is a word normally you use. Multi-programming means ability of the operating system to load multiple programs simultaneously. Right? The OS is designed so that it can load multiple programs into the memory. That means in some area of the main memory, one program is going to be loaded. In another area of a program, another area of a memory, second program can be loaded. And naturally, one need to protect one program from going into another program and disturb it. So we should actually take care of all those protection mechanisms as a part of design of the operating system. Single user cannot keep CPU and IO device busy at all times, right? Strictly speaking, single program, actual user here in the context of single user cannot keep CPU and IO device busy at all times. Multi-programming organizes jobs, code and data. So CPU always has one to execute. When you have multiple jobs, then it is possible. So that CPU can take one program, devices might be busy on other programs. So that way you are making all the components within the computer are going to be busy doing something or the other. Thereby, like you are going to get more productivity. You are going to get more productivity. In fact, this used to be the case, as I said, in the early days when the cost used to be so high, and naturally You have to increase your efficiency. A subset of total jobs in system is kept in memory. Right? So job means program actually. Earlier days, people used to call them as jobs. One job is nothing but code along with the data that is required for running. A subset of total jobs, total programs in system is kept in the memory. One job selected and run via job scheduling. Right? So you need to schedule, right? So that means which job to be executed there and all that. And when it has to wait, for IO example, operating system switches to another job. This is the multi-programming means. Batch system and all this is related to your mainframe, where right? So you have to, like in those days, in fact, people used to write programs. They don't actually run their programs. So you have to write your program and give that program along with data to another specialized people. And they will actually compile your program. They will run the program on the data what you are going to provide. So different scenarios used to be there earlier days as a part of it. So you have to give your program and data today, and you have to go there to a specific computer center next day and collect your results and all that particular thing on a computer printout kind of thing. So those are the terms that you are actually seeing here: job scheduling, batch systems, and all that. Time sharing or multitasking. Multitasking means actually again the ability of a single user also can supply multiple programs. How are you going to get multiple programs into the system? Either several users are connected, each user is supplying a one program, and then all the users' programs are loaded into the system and run. Multitasking means actually single user also can submit multiple programs. That means actually you can submit many programs in a background so that they can be executed in the background. There can be a single program running in the foreground, normally you call it, using interaction and all that, right? So a logical extension in which CPU switches jobs so frequently that users can interact with each job while it is running, creating interactive computing. See, this interactive computing, even though now, like you can't even imagine how can it be non-interactive. How can somebody else give the data that is required by your program? But all that imagination you have to provide and then give all the data to the user, to those specialist data entry people or computer experts who used to run the programs those days and all that. Right? Whereas now interactive, multi-user, all that. So users themselves are going to compile, they themselves are going to run all that. Response time should be less than 1 second, especially when you are talking about multi-user. Like when several users are there, every user should feel as if his program also is being running. So what will happen sometimes is that probably a program might enter into an infinite loop, let us say. There are four users, and 4 users' programs are submitted to the computer. One of the user has submitted an infinite loop program. If that program is taken by the computer, then it will go into the loop. It will never be complete, so that it can come to the other programs and all that. So you have to design your operating system so that none of these things is going to affect the performance of the other users. So you require some kind of what you call time sharing. That means your CPU must be designed such that it's going to pick one program and execute for not more than, let us say, for not more than 1/10 of a second. Run the instructions of this program for not more than 1/10. So whenever it actually crosses 1/10, switch to another program. So you are actually sharing a time. Switch to another program, run for another 1/10 of a second, go to another one, and so on. So after some time, you will come back. In this way, even if one of the user writes an infinite loop, his code will be executed for not more than 1/10 of a second, and then go to the other users also. So that's what you are actually talking about. Response time should be less than 1 second. Each user has at least one program executing in memory process. If several jobs ready to run at the same time, CPU has to schedule. If processes don't fit in memory, you have to swap the instructions and data from the memory into the secondary storage and again come back. And virtual memory allows execution of process not completely in memory. We are actually talking about various computer organization principles and also operating system works, virtual memory. So layout for multi-program, this is how it is. So if this is the main memory that you have, 512 megabytes, assuming that that is the data that you have, that used to be very large in those days, 512 MB main memory, but now it is running into gigabytes. So in the initial portion of the main memory, operating system is loaded. And this is always there. Only these programs and instructions in this remaining area will come and go. So assuming that like it is supporting multi-programming, you are loading job 1 here, 2 here, 3 here, 4 here. That is what you mean by it. And the CPU will be executing all that. So interrupt-driven hardware and software, this already we have seen. So what is meant by all that? And operating systems normally, they run in 2 different modes. One is the user mode, the other one is the kernel mode. So only the programs that are executed, normal instructions of the user, they will be executing under user mode. And whenever you make a call onto any service related to operating system, it enters into kernel mode. All the system services are provided running at kernel mode actually, because you need to have access to the kernel data structures and all that. Normal user mode cannot access all that. That is what you are actually talking about, dual mode. Dual mode operation allows OS to protect itself and other system components. User mode and kernel. Mode bit provided by hardware. So whenever it is about to provide the system service, the mode bit will be set and then go there. So that you are going to get access to various other data structures, kernel data structures and all that. So when you are again coming back to the, like from the system service, so mode bit will be reset so that you cannot access the data structures that are there within the operating system. Provides ability to distinguish when system is running user code or kernel code. Some instructions designated as privileged only executable in kernel mode. Privileged instructions. System call changes mode to kernel, as you can see. System call changes mode to kernel. Return from call resets it to user mode. That's what you really mean by it. So all the instructions that are there within the system call service, they are all privileged instructions, which have access to the kernel data structures. Increasingly, CPU support multi-mode operations. So you have virtual machine managers, mode for guest virtual machines. This is another one. So far dual mode. Now the existing CPUs have even multi-mode operations. Because nowadays, you can have a host operating system, you can have a Windows operating system, on that you can have a virtual machine, meaning that you can run both Linux as well as Windows simultaneously and get a feel of it these days. And that is possible by using virtual machines. Virtual machine operating system related stuff. So you will have a host operating system, a single one, and then you will have several guest operating systems, and one can work on different operating systems simultaneously. It's not dual boot. Dual boot is different. In a dual boot, at any point of time, either you can work on OS 1 or OS 2. Whereas in virtual machines, you can work on multiple operating systems simultaneously. In such cases, you have multi-mode operations, switch is going to be provided. And transition from user to kernel mode, what you are actually having, you can see here. This entire thing is the kernel area data structures, and user process is running, user process executing, call to a system call. Then a trap, mode bit equal to 0, run this, and again reset, like this. This is what you really mean. Same thing is explaining here in a diagrammatic fashion. Process management, like so how are you going to manage the processes and all that? A process is a program in execution. See, program, for example, you compile it. Compiled program is available on the disk. It doesn't mean that anything is happening. Nothing happens. Only when you initiate running the program, only then the results, you can see the results. So a program in running state, a program in execution is actually called as a process. It is a dynamic mechanism. Process is a dynamic, program is a static kind of entity. Right. So it is a unit of work within the system. Program is a passive entity. That's what he is actually talking about. A process is an active entity or a dynamic one. Process needs resources to accomplish its task. So a process requires CPU to be executed. It requires memory to store its data as well as instructions. I/O devices for reading data and all that. Files and all that. Initialization. So everything. Process basically needs resources. So whenever you initiate a process, it is the OS, operating system, that is going to allocate all the resources. And when the process is terminated, the operating system will take back all the resources. So process termination requires reclaim of any reusable resource. Single-threaded process has one program counter specifying location of next instruction to execute. Again, there is the concept called as multi-threaded. Within the same, a single program may contain multiple threads, so that when one thread is actually waiting for something, within the same program, a different thread can take over and then run it. So that the program is going to get a lot of its share and productivity can increase. So that's what you actually have something called multi-threaded processes. As one program counter per thread. For every thread, you require a separate program counter. Typically, systems has many processes, some users, some operating system running concurrently, right? All those threads, all that related stuff. Process management activities. You can have create a process, you can delete a process, both user and system process. Suspending and retrieving, providing mechanisms for process synchronization. So all those related stuff you can actually see. Memory management, to execute a program of the instructions, like sometimes you want to have more data, so there must be a mechanism, right? So normally you must have seen like how to actually dynamically request the operating system for more memory. So even in C language supports that by doing BRK, memory BRK kind of operations are there by which you can extend the memory. MCPY also is there, all that. So allocating and deallocating memory space as needed, keeping track of which parts of memory are currently being used, all that. There is a memory management segment. Similarly, secondary storage is storage management, file system and all that. There are different types of file systems. So one can make use of it so that you can create files, you can retrieve information, you can copy directories from one to another. All that kind of support management is done by storage management. Mass storage is external storage for taking backups and all that, that particular mechanism. So this is the other time we were talking about levels, right? Level 1, level 2, level 3, level 4, level 5. Levels of storage. So level 1 storage is called as registers, level 2 is called cache, level 3 main memory, level 4 solid state, level 5 magnetic disk. Typical sizes of the memories, registers may be less than 1 kilobyte. Right? Registers means 64-bit register or 128-bit register, even if you have it. Right? So when you add all the registers capacity together, it may not cross 1 kilobyte. That's what you are actually talking about. These registers are a part of the processor itself. Cache, a little bit like nowadays within the same chip you are going to get, but it's not a part of the processor. So it is of the order of 16 megabyte maximum kind of it. Main memory 64 GB, solid state 1 terabyte, magnetic disk 10 terabyte, so kind of thing. But these figures, they vary from time to time. They are not standard all the time. But what is important is that, so from one level to another level, they will be of orders of bigger in size. So 1 kilobyte to 16 megabyte means it is 16,000 times bigger. So this 1,000 times bigger is always going to be maintained. So similarly here megabyte and gigabyte. So this is again another 1,000 times bigger. So here also another 1,000 times. Here about 10 times. That kind of stuff. So what is the underlying technology? You can see here using CMOS technology is registers here. On chip or off chip CMOS SRAM, static random access memory. DRAM and SRAMs, normally we call them. So SRAMs here, and CMOS SRAM again, main memory also, right? On chip or off chip, it can be. This is always off chip only. This is a flash memory also. Solid state disk, they are also sometimes called a flash memory. And then magnetic disk. Access times, as you can see in nanoseconds, you can see here. 0.25 nanoseconds, you can access a particular byte within the registers. Cache 0.5 to 25 nanoseconds. You can see here itself of the order of 2 times 2 or even 100 times. So that kind of significance. Main memory 80 nanoseconds. This thing. Solid state you can see, then magnetic disk of several orders. That's why. And bandwidth, what is the bandwidth at which you can actually this thing? How many bytes you can actually transfer within a particular second? Naturally, if the access time is lesser, bandwidth will be higher. 20,000 to 20,000 megabytes per second to this, and so on. Managed by compiler, hardware, operating system, and all. Backed by all this. So these are the some of the characteristics of different memory storage. Migration of data A from disk to register. So all this is there, several copies of data or whatever. I/O subsystems. Protection and security is another thing that one may have to. Kernel data structures. So portals and all that, mobile. Computing environment, just now we have already talked about. Client server environment is nowadays very order of the day. Like your browser is a client, the server running at the like Google or Yahoo or your JNTUH, those are the servers that are providing the web pages requested by your browser, right? It is a client server model. So basically a client program, server program. Client program running on one machine, requesting server program running on another machine, or maybe on the same machine also, over a network. That's what you really mean by it's a very popular model using which many things are happening over the network. So you need to understand what those things are. Compute servers, file servers, all that. Peer-to-peer is another thing, meaning that there is nothing like client and server. Every client here will act both as a client as well as a server. That's what you really mean by. So each one is going to do both the things. P2P, peer-to-peer, you normally call it. Especially like Skype is there. Skype is a peer-to-peer kind of thing. So here and here. Similarly, data management like music servers and all that, they are also peer-to-peer kind of thing. So what you really mean by is that, for example, music, you want to store your music files within your system, and you want to give access to the other people. So you have a software program running here, similar capabilities. These things will talk to one another, and share the music. So this fellow may have a file that is not there here, so he can make it available to him, and this fellow can share it. So such kind of peer-to-peer networks, popular networks are possible. Virtualization, just now we said virtual machines and all that, right? VMware is a popular software program using which you can load any kind of operating system onto VMware and run it, right? Any number of guest operating system can be run as a part of it. I think we will continue the other things the next class. Maybe it is running into more time. Normally you are not used to, and it is a day end. I don't want to do that. But I think I request all of you to download and start reading this material. If you have any questions, like after reading that, we can actually talk about in the classes also. Next class, we will actually see the other things. Do you have any questions or whatever? I have not asked so far. If you have anything specific, you can. Otherwise, we can close it. But try to download and start reading the material. Tomorrow is a holiday, so Mahashivaratri. So I think we will not have any class. Next week only, again, Wednesday we will meet.